Guys, hello. I'm Dmitry Gushchin. Your lecture for this course for this semester, and I have two assistants that are in chat in Telegram. Their name Follow and Yesenia, and they send you tasks in Yandex contest that you will need to do at home. As I understand, in the previous semester you did Yandex contest too, yeah? Yes. Nice. So lecture 1, graphs and breadth first search. Firstly, I will ask you what you know about graphs. Do you know anything? What? As I know, you know what is binary tree. Yeah? Binary tree. And other classes of graphs or linked list. For example, linked list in graph is equal to path graph. Okay, other?
You mean a graph data structure related to graph?
Yeah. For example, other structures or classes of graph. Okay, and do you know definition of graph?
Yes.
What is the definition of graph?
A graph is a set
Okay.
of
Let's start. This definition of graph, it's a pair of two sets, vertices and edges. As you see, V means vertices, E means edges, logically. Yeah. So it's picture of graph, and of course there are any other definitions you can see in books, in Wikipedia, for example. And we set this definition because we will work with today only one class of graph, and on the next lectures we will work with other classes, but they all contain in this definition. But for example, you can see now that on the figure there is loops, there is multiple edges, and we will think that graph has no these edges, and other definition, there is two main classes of graph that you need to know: directed and undirected. Directed graph usually figure out as vertices as circles with arrows between them, and as you know, there is edges between two vertices that can connect D with E and E with D. There is no contradiction, yeah? Guys, do you understand? It isn't multiple edges, yeah, because they have different directions, yeah. And you see a formally definition on the upper of slide that every edge we can code as start vertex or vertex and end vertex. Yeah, it is endpoints of edges. Okay, guys, nice. And second class of graph, it's undirected graph. Yeah. What's the difference between this definition and previous? What?
The first definition between two edges between two nodes, but this one there is only one. Either they are linked or not. In the previous one, they may be linked from left to right or right to left.
Mm-hmm. Okay, and I can say, as you say, that this pair of vertices, yeah, x and y, has no order. You see? Brackets. Brackets on this slide and brackets on the previous slide. When we draw x and y in these brackets, it means that they have order.
The order is important.
Yeah, it is important. Edges have order or no. And if edges have, it is directed graph. If they have no order, it is undirected. Okay? Understandable? Okay. And of course.
Can you go back to
Oh,
the first definition?
yeah, yeah. This?
No.
This.
Directed.
Yeah.
So a node can have a link to itself. Cyclic, a node can have a link to itself.
As you see, x not equal to y, and so there is no loop.
X to X.
Yeah, there is no loop in a set of edges because x not equal y. You see?
And then,
It's condition.
could you explain the expression ends of the edges are not equal?
And ends edges not equal. Formally,
Yeah, for example, just to...
as a picture, you can see on this picture there are loops from M to M and from D to D. And we cancel this ability.
This is not possible if
Yeah. Yeah.
this is another thing.
So, okay, and of course there are a lot of types of graphs. We will talk about, for example, bipartite graph, weighting graph, tree, for example. But of course, you don't need to know any of these classes. But of course, you need to know to these classes. Okay, undirected and directed. Because they're important, all graphs that we talk about will be directed or undirected graph. Okay? And we will think that today all graphs simple. That's graph has no multiple edges, loops, or etc. As you see, different edges. And today we'll work with these graphs, yeah, where edges is an ordered pair of vertices, and there is only one or zero edges between two vertices. Okay?
Sorry,
You can have loops, right?
Loops?
Yes.
No. Undirected has set of edges where edges.
Yeah, I noticed, but usually you can. For example, when we study
If you present a loop, you can see formally it's multi-set, yeah, with x equal to y, yeah. But formally we formally we say they are not equal, so there is no loops. Formula. Okay. And other definitions that you need to know, it's simple definitions that we use during today or using on the next lectures. But if you don't know this terminology, you need to know on the next lectures, for example. Okay. And these slides I will send to you in chat, so you may to repeat the slides and so try to understand definitions. Okay. It's about adjacency, yeah, of graph. Yeah, adjacency is equal that there is edge between some vertices U and V. Yeah, okay. So when we talk about graph in programming, we want to understand how to get graph, get algorithms on graph, yeah, and put it in the computer, of course. And there are three different ways to do it: adjacency list, adjacency matrix, and incidence matrix. And did you face with these representations earlier? Yeah. Did you face with this?
Incidence matrix? No. We had only incidence matrix. We didn't face it before.
And adjacency list and adjacency matrix?
Just adjacency matrix and I think adjacency list. Incidence matrix we did it.
Okay, yeah. So we can repeat that adjacency list. It's list of linked list, yeah, where every row is equal to vertex, and there are all vertices that adjacent to vertex. For example, in the first row, we see its row equal to a vertex, and we see on the figure that A adjacent to B and G. So in the linked list, in the first row, we see B and G nodes. Okay, and etc. We see other rows is equal to adjacency of each vertices. Okay. Have you any questions? Do you have any questions? No?
Adjacency list can be also represented as something like hash map.
Yeah, of course. We can store sets of adjacent vertices in different way. It's first simple way to store as linked list. Of course, we can use, for example, set. It is also data structure, or as you say, we can use some arrays, yeah, and use hash for hashing this. Okay, Yeah.
One question.
Yeah.
What makes NE?
NE. Okay. As you see, node, it is name of vertex, and it is a reference to child, for example. Child. No, it's equal to adjacent vertex next from this. We see first node, yeah, has arrow to second with name B, and so we say that A connected with B, A adjacent to B. And for example, G has null reference because there aren't any other vertices connected with vertex A, for example, in the first row. Okay.
Then you can say A connect to G and then G will be right. Just we flip B and G.
Flip.
We can see it.
Okay. Yeah, of course, there are different representation of this linked list. Yeah. As you can implement this adjacency list, you can use different ways to sort these nodes. For example, you can use lexicographic sorting, yeah, and you see these nodes has lexicographic sorting, lexicographic order, yeah. But it's interesting when you use graph, yeah. What you want to do with this graph, because if you want to delete nodes, and for example, you use this graph in parallel mode, yeah, and you can delete several nodes in one time, yeah. You can understand how to contain this linked list, to understand to cancel different mistakes that appear if you use parallel methods. Okay. So of course there is different ways to store every row. Okay. Then adjacency matrix. Yeah. It's matrix with dimensions n equal to number of vertices, and as you see, every element of matrix is equal to adjacency between a row and column. Yeah. And for example, do you know what is advantage of this representation than this?
This is the reference of one. The grid adjacency matrix is very fast. So now the
Yeah, we can remove edges quicker than in adjacency list. Yeah.
here we need to, it's linear time.
Yeah. It's linear O from number of vertices, yeah? But here it's equal to O notation O from 1, yeah?
Yes.
Okay, but what is advantage of this representation? Space, of course, yeah. We can see there are only space complexity equal to O from number vertices plus number edges, yeah? Yeah? It is true? space complexity equal to number of vertices plus number of edges of this representation. We can see there is O from number of vertices rows, and summary, yeah, in each row we have number of vertices equal to degree of vertex, yeah? Plus 1. And number of nodes in this list equal to sum of this sum, yeah? And what is its sum?
It's equal to sum of x, all x.
What?
It's equal to number of x plus number of nodes.
Yeah, but sum of degrees equal to 2 number of edges. Remember? It's 2 number of edges and number of vertices. Do you remember why some summary of degrees of vertices equal to edges plus edges? No? Forgot, okay. So let's repeat. And I have a question in chat. What is O notation?
Why is the sum of degrees of the vertices plus 1? Why the plus 1? No. Yeah.
Plus 1? You can see, for example, degree of vertex A is equal to 2, yeah? And in the list we have A, B, G nodes. With, you can see there are 3 nodes. Okay, and it's about O notation and this theorem. Okay, now I clear this board and write down proof of this equality. Okay, and so firstly, I have a question about O notation. Do you remember O notation? What is it? Function is equal to O from function f equal O from g function. Do you remember? What is it? F and g, for example, some functions from natural numbers to positive real numbers in G2. What is it? By definition, of course. Or have you faced with this notation? F of x equal to zeta of g of x. Do you remember? Space complexity of in calculus, it is f divide g of x. No, you're not right.
Big O is upper bound.
It's about big O.
Yeah, it's upper bounds of f. But formally, what is it?
Formally, it's
there exists number n big that for all n bigger than n the function n multiplied by c. Oh? Please repeat, yeah?
Less.
Yeah. F. Yeah. F of n less than c multiplied g of n. And of course there is c. Yeah. It is given in this inequality. Remember?
This is the definition of
Yeah. It's definition of upper bounds and all notation. Okay, and this by definition. Do you know definition of this notation? Yeah, of course. Yeah, there exists number n big. Nature, of course. There exists c big and c small, such that for all numbers bigger than n big, function f of n smaller than the big multiply g of n. There exists n natural number. Exist c small, c bigger than 0, such that for all n small natural numbers that bigger than n big, there is true to inequality. Okay? Other questions about its what's bound this?
It's called theta.
No, yeah, it's Greek theta, and it's equal to concrete bounds. Did you hear this name, concrete bounds? Yeah, it's equal to upper bounds plus lower bounds. Okay, and now I clear both, and we'll write down proof of theorem that summary of degrees of vertices is equal to twice number of edges. Okay? Yeah. Can I clear? Yeah? Okay. So, theorem, it has name first theorem of graphs, and so if we have graph G equal to pair of V and E. Of course, finite graph or undirected. Without multiple edges. And loops. Then summary of degrees is equal to twice number of edges. Okay. Okay, proof. Every edge E equal U and V. We divide into two half edges. Yeah. O and into two pair. Yeah. We remember which edge we divide, and it is one endpoint, it is other endpoint. Okay? So, what is the number of half edges? Yeah?
Can you use another letter instead of E?
E?
Because we already have E.
Yeah.
Where? This?
No, down. Yeah, yeah. This is the
And is this? They're equal, of course. I can.
Yeah, just like just the name of the vertex. We just make it different just because it's.
Of course. And it is not vertex. It is half of edges, and we remember endpoints and edge that we divide. I can draw a picture, but can you turn camera? Thank you. For example, yeah, we have graph. Yeah. For example, A, B, C, D. And what is the set of edges of this graph? A, B, B, C, okay. Okay. CD, okay. And now I can divide all of these edges into half edges, yeah? And set of half edges we remember A, and we remember edge that have that has endpoint equal O. I need to connect with chargers. 1 second, please. Can we move it?
No, it's him.
No? Nope. Okay.
This one is blocked.
Yeah. See. Okay, and so now we can move it.
Yes, it's different.
Nice. Whew. Okay. Now, yeah, it charges. Okay. Then the set of half edges. We can name it as E1, E2, E3, E4. Okay? And first edge divide into two half edges, A, E1 and B, E1. Okay? And second, B, E2, C, E2. And etc. Okay? So, what is the number of half edges? Logically. Twice edges. Yeah? Okay, this set will be K, for example, and logically number of elements of K equal to twice number of edges. Yeah? But we can see how many half edges that connect with vertex, for example, B, we have. It's equal to degree of vertex here. There is 3 edges, half edges. Oh, yeah. There are 3 half edges, and it is equal to degree of vertex B, okay? And there are 2, and equal to degree of vertex D, etc., okay? So this number is equal to summary of degree of vertices, okay? And it ends the proof. Understandable? Nice. So, of course, we return to our question, what is the space complexity of adjacency list? It's equal to O from number of vertices plus number of edges, okay? Because in each row we see a number of nodes is equal to degree of vertex plus 1, yeah? So we need to use number of nodes equal to summary of degree of vertex plus 1. It's equal to twice number edges plus number of vertices. It's equal to O from number of edges plus number of vertices. Okay? Nice. It space complexity of adjacency list. And what is the space complexity of adjacency matrix? Yeah. You're right. It's equal to O from number of vertices in square. Yeah. Okay. And what is better? And it's different. It's different upper bounds or no?
Yes, different upper bounds. Or
Is it different upper bounds? Or we have graphs that has similar upper bounds for this representation and this.
what?
Do we have any classes of graph that have equal upper bounds in this case and in this case?
Yes, that is linear space, linear O of n, and this one is O of n square.
When the number of n is equal to the number of
Number. No, in this way, when we have very small number of edges is equal to vertices multiplied by constant, we have this linear complexity and this square, and they are not equal. But when they're equal,
We can okay, when
if
there are many
there is
all
the number of
connected,
edges.
all vertices are connected with each other.
yeah, it's only one graph. But you can say that when edges similar to v n square, yeah? Because in full graph, can I clear this? Yeah? What? Can we show directed graphs with adjacency list? Okay, Masud, I will get example after we talk about it. So, about complexities. Yeah, if we have nearly full graph, it's equal to represent it as adjacency list or adjacency matrix. Okay. But for example, if we want to set weight, for example, of edges, we can use adjacency matrix to get the quicker way to change weight of edge. Okay. And for example, there are different algorithms that have weight in graph, yeah, as you can see on the previous slide. Previous, yeah. Weight in graph, yeah. When we set weight as a number that have every edges, okay. So.
Here
Okay.
it doesn't show everything. Here it doesn't show.
Oh, I see. As understand.
It doesn't show this. Or to call them to fix it.
No. No. I don't know.
I'll write them, they will come to fix it.
Oh. I don't know how to resize it. Okay. So, as a result, when you use graph for concrete task, you need to understand what methods you need to use or what parameters of graph we have. For example, if we have very sparse graph, yeah, where edges is equal to number of vertices, yeah, of course we don't need to use adjacency matrix because it's very complex to use a lot of memory. Okay, so about directed graph and adjacency list. So about directed graph, example of adjacency list of directed graph. For example, we have 6 vertices and yep, A, B, C, D, E, F. So we start every row as node with name of vertex. Yeah. A, B, C, D, E, F. Okay. Then, for example, for A, only B. Yeah, we see what is the vertex that we can join from A. That is reachable from A. Yeah. In one move. Only B. Okay. For B is only C. And we don't write down the A vertex because it's directed, it's edge with order, and we cannot move from B in the different direction from the direction of edge. Okay? So for C, only D. For D, there are 2 vertices. Yeah. Okay. For E, only F. For F, only E. Yeah? Understandable? Guys? Nice.
Why DCE? Could you explain that?
DCE, why? Because we have 2 edges from D to C and to E. So we have 2 nodes equal to 2 vertex that we can reach in one move from D.
It doesn't mean that C first C and D doesn't mean that is the other.
Or connect?
Yeah.
No. You can see at these rows as name of vertex that have some adjacent vertices, and this is adjacent vertices to V, yeah? Where V is equal to first node. it doesn't mean that C and E connect in our graph with H. Okay? So, next slides. Of course, incidence matrix. Okay, and now, interesting question. What is the advantage of incident matrix than adjacent list and adjacent matrix? As we can see on the next slide, yeah, we see time complexity that we need to spend on the operations or graphs, yeah, and we can see incident matrix has a lot of difficulties with it, yeah, because in the worst case, what is the upper bound of operation? Number of edges will be equal to number of vertices in square, yeah, and multiply by number of vertices. We understand that operation spans number of vertices in third power, yeah? Understand? No? I need to repeat.
When it's third power, we're talking about directed graph. Non-directed graph should be second power.
Oh. No. When number of edges similar to number of vertices in square, then upper bounds number of vertices multiplied by number of edges equal to upper bounds of number of vertices in third power. Yeah, it's very bad asymptotics. But there is only one advantage in incidence matrix than in others.
Can you show us the incidence matrix representation, how it works?
As you can see, there are 7 edges, so we have 7 columns. Each column is equal to one of edge. And each row is equal to one of vertices. Yeah? And in column we have 1 and 1 on the intersection of column and rows that this edge connect. For example, first edge, yeah, incident to A and B. So we have 1 in first and second rows. Yeah, understand? Okay. And what is the case when this matrix is better than this matrix and is better than this list?
If we are talking about weights,
If
we are making use of weights.
I think
weights. Weights, we can use adjacency matrix too. Do you know any cases? Okay. My hint is to see on this slide, or for example, this slide.
Yeah, I think monthly is.
For example, this. In the common case of graph, we can have hyperedges. It's subset of edges of vertices. Yeah? So if we have hyperedges, it connects more than two vertices. But matrix, adjacency or incidence matrix, they say that edge connect two vertices and have, for example, weight. Yeah. So if we have hyperedges, we can use incidence matrix, and we can set more than two rows equal to one or bigger number. Yeah. For example, if we have a graph with standard edge, yeah, a subset of two vertices, and not standard edge, a spinner, yeah. Okay, and for example, A, B, C, D. E is equal A, B, and B, C, D. Okay. So, incident matrix will be it first, for example, it second. We have 4 vertices, and this 1, 1, 0, 0, and this
0, 1, 1.
0, 1, 1, 1, yeah. Yeah. More than 2. Yeah. Vertices connected by this edge. So all of these presentations you can use in different exercises. Okay, do we need 10 minutes to sleep or go to the coffee? Yeah? Okay. So I stop lecture, and if you have questions, you can ask, for example. Okay. Yeah, we can power in N, and this matrix contains some information about paths in graph, and we will talk about it. And for example, this algorithm use one of these concrete representation. Yeah. So if algorithm has no specification about representation of graph, you can use one of them that you want, and that have more complexity adventures. Okay. So then we talk about paths, and we talk about breadth first search. It's some definitions that you need to know, and the most useful last two definitions, path and cycle. If we see graph, yeah, graph very similar to web of transport system, yeah? And for example, there is city A, city B, and logically this path from A to B, yeah? And you can see definition is equal to a priori understanding of this word only. Yeah. But of course, graph theory contains other two definitions, and if you see trails, walks, it's nearly equal to path, but different in formally way. Okay. So after lecture, if you don't understand difference between them, you can ask me and I say it. Okay. Now we need to face with this. Okay, and of course about cycles, about history of graphs. First using of graph theory was in 30s of 18th century, and it was first step in development of graph theory, and of course now we have a lot of different characteristics, algorithms that connect with paths and cycles. Okay, and we will talk about the different cycles, paths, and algorithms connected with it. So it's only historic view on the problem. Then, yeah, about distances. If we have, for example, this graph, yeah, we can say that distance between two vertices is equal to number of edges in the shortest path join them. Yeah. For example, distance between vertices A and C equal to 2. Yeah. 1, 2. Yeah. 2 edges. And for example, distance between A and D. No, not 4, not 3. You say 4 because you have this way, yeah? From A to D. But we have shorter way from A to D. Yeah?
But it's a rule. We always should choose the minimum. Yeah, it's in the definition.
The shortest path.
The shortest meaning.
Yeah, it's important that it is the shortest path. So it's equal to 3. Yeah, and there are 3 properties that say that vertices with this symmetric function is symmetric space. Do you know what is symmetric space?
Yeah, that's the question. Why? Just to, because
Why?
The metric space is, you mean the definition like in the
Okay, and do you know in a common way what is the metric space?
Yes.
What is it? No.
Yeah, we just
Yeah.
had some property.
Yeah.
On the calculus you didn't have. You
We
have metric space, yeah? And you say that it's metrics that have properties 1, 2, 3, yeah? So if we set distance and try to prove these 3 properties, then we say that it is metric space, okay? So this theorem is equal that these three properties are true. Okay? Do you understand why first and second properties are true?
Because same point.
Yeah.
Second one is
Just because
Base from because undirection of graph, yeah? Because graph is undirected. And the third? Understand? Because we have and we have path. This path that has length equal to distance between U and V, yeah? And we have path from V to W that's length equal to distance between V and W, yeah? And we can connect these two paths, and we have paths from U to V with these distances. But of course we can have other paths that can be smaller than sum of these two paths. Okay? So it is inequality.
Like triangular inequality.
Length?
Triangular inequality.
Yeah. Triangular inequality. Yeah. Okay. So there are metric characteristics connected with distance. We need to understand only one of these characteristics. It's the last, diameter. Yeah. If we see it, maximum of eccentricity, and max eccentricity of vertex, it's maximal of distance to other vertices. Okay. And for example, we can see in this graph, yeah, the maximal distance will be between A and B. Yeah, it's equal to 3, 2. And other distances between two vertices from this graph smaller than 3. Yeah, so it's diameter of graph. Yeah. Because you can input definition of eccentricity in definition of diameter. Yeah, and you see that this diameter maximal over choosing two vertices and distance between them. Yeah? It's the consequence of these definitions. Okay? It's maximum of distances of two vertices. Yeah? Vertex V is given, yeah, and then we can calculate distance to other vertices. For example, from E, we have vertices on the distance equal to 1, on the distance equal to 2, and 3. Yeah. So eccentricity of vertex A is equal to 3.
Okay, so when you talk about eccentricity, you talk about 2 points, one vertex and another vertex.
Yeah. Not 4? Where you can find distance equal to 4?
From A, right, down, left.
And now we remember the shortest path. It's important. Okay. And it's one of the characteristics of graph, and graph theory contains a lot of characteristics, and we will face with others, but now we will talk about diameter, for example, and we will talk in applications. Yeah, when we can face with graph. Yeah, you can face in web crawling, network broadcasting, routing, and other ways where we can build model that contains graph. Okay. So, for example, about checking mathematical conjecture, you have a way to transform one formula to other formulas. Yeah. So it's directed graph because formula is a state, is a vertex of the graph, and if you can using mathematical transformations, using them transform one formula to other, you can say that they're connected, and you can get one hypothesis, for example, and say that other conjecture is true. Okay? For example, about checking mathematical conjecture. And for example, solving puzzles and games. Yeah? We will talk about cube. Yeah? For example, pocket cube. It's cube 2 times 2 times 2. Yeah? And we see that it has 8 smaller cubes, yeah? And if we want count states of this cube, we will get nearly 3.5 million of states. Then it's a very small graph, of course, and we can understand what is the structure of graph. Yeah? For example, we have solved state. What is it? On the figure, yeah? It's solved state. Then we can make transformation of cube. Yeah?
Like a neural network.
Or like neural. Yeah, it's similar to neural network. Yeah. And first wave of vertices, yeah, equal that they're equal to states that we can get when we use one move. Yeah. Then when we use 2 moves, we get second waves, etc. And diameter of this graph, it's the maximal permutations, for example, that we need to use in the best way, of course, to go from this vertex to this. Yeah. So, for example, to pocket cube. For example, to pocket cube, diameter of this graph is equal to, do you know? Some hypothesis? Okay, graph contains more than 3 million of vertices. And what is the diameter? The longest path between 2 vertices.
It can be. I don't know how to visualize pocket cube in graph. First of all, the simple solved form. Solved state. How does it? How can I see represent cube in graph? That I can't.
Oh, okay.
Basic form.
You can fix pocket cube, yeah, and you see every corner of cube, every small cube. And this, for example, order of 8 numbers. And every corner you can transform into 3 positions, yeah, from permutations. So you can code your state of cube as 8 numbers that equal to every smaller cube, and 8 numbers from 1 to 3 that say you need to transform your cube or set it as in the picture. So it doesn't matter how it counts, but you can understand that it is finite states. Yeah, you have cube, and there are only finite states that we can get when we transform it using our brain. Yeah, and then we have finite states, and we connect with edge them to 2 states when we can get from one state to other in one move. Yeah. So, what is diameter? Of course, it's difficult. I didn't understand what you said about the cube. Masoud, can you set more concretely what is the point I need to repeat? Yeah.
Maybe 1 million.
Hmm?
1 million something like that.
One begin?
1 million.
1 million?
Yeah, I don't know.
Oh, and you see 3 levels, yeah? And I think that 3 million divided by 3 equal to 1. No.
It's 2 times the maximum level.
See, if these 3 vertices, this will be nearly 3 in 3rd power. Because from 1 we have 2 edges, for example, yeah? And for example, we have no similar vertices here, yeah? And it's exponential. So diameter of pocket cube is equal to 11? 11. Understand that we have more than 3 millions of vertices, and its graph has diameter equal to 11. Yeah? But it's not full graph. Yeah. So it is of course a computing exercise, and we have algorithms that can solve this task in the best way, yeah. You can send this algorithm sum of state of cube, and algorithms say you need to transform in this way, in this way, in this way, and then you get solved cube. Okay, but if you get, for example, not pocket cube, for example, cube, Rubik's cube, yeah, 3 times 3 times 3, yeah, numbers in states, numbers in number of states is equal to billion of billions. And of course, it's very hard to get graph, yeah, and count diameter and count paths between them. But of course, we can use locally algorithm. Yeah, for example, algorithms that say, oh, we sit here. Yeah, so we can see for adjacent positions and say what is the best position and go to them. And in the best case, in the best way, we go to soft state. But for Rubik's Cube, you cannot compute, you cannot get program of algorithm of that solves this problem. But now, 5 years ago, there was an article that make a point on the God's number or diameter of this graph in Rubik's Cube. It's equal to 12. Yeah. Oh, sorry, not 12, 20. 20, yeah. And interesting that we have billions vertices, but diameter is equal to 20. Okay, and it's about tasks and applications of finding paths. Yeah, so we can say that problem of finding paths between two vertices very often problem. Yeah. For example, for these tasks. Yeah. And we have a lot of companies that have maps, for example. We have companies that have some computers and need to get algorithms that find distances between vertices in the best way and very quickly, of course. Yeah, because if you open maps, you want to understand what way you need to use from, for example, campus to the center of Moscow. Yeah, and you don't want to wait for 1 hour when your computer computes all of the ways from campus. You want to set points on the map and then in 5 seconds, for example, get answer. Yeah. So it's very important to get answer on the question what is the shortest path between two vertices in a very quick way. Okay. So about breadth first search. Idea of this algorithm equal to waves on the sea, for example, or ocean. Yeah, you can see we have center of wave. Yeah, and, BFS. Yeah. Breadth first search. And yeah. Yeah. Breadth first search. Shortly BFS. Yeah. Yeah. About idea, yeah. You have center and waves, yeah, of this searching. So concrete algorithm, you set center. It vertex that we are given, yeah, and then we see in the graph and see what is the adjacent vertices of this V vertex. Okay? For example, if it is V, yeah, it is adjacent vertices to V. Then we say that distance to them equal to 1 and add them into explode, into new explode array, and pop out vertex V. Then we repeat this operation for these vertices. Yeah, we repeat, for example, for this vertex. Yeah, and we add these vertices into explode and set that destination from distance between V and this vertices equal to 2. Yeah, and repeat it while we can do it. Yeah, so it is formally mathematical algorithm, and it is implementation on pseudocode. Yeah, for example, in the first three rows from 2 to 4, yeah, we said that we don't know distance between V and other vertices, yeah. Then we say that in 5 and 6, we say that we know that from S to S there is distance equal to 0, yeah.
The goal of BFS is to explore all the vertices or to calculate the distance?
Yeah, thank you. Good question. BFS has goal to understand distance between S and other vertices, and S is given before we start our algorithm.
Some vertices.
Yeah, yeah.
Distance between?
S and other vertices.
And S is the center.
S is the center, yeah. Yeah, in...
Between S and which vertices?
Oh? Yeah.
Between S and which vertices?
In this picture, S is the center of graph. And we, on the start of our algorithm, we get graph and center. And then when we find distances between center and other vertices and return it after algorithm.
We return the distance. We return the distance.
Yeah. Between S and other vertices. I can get you example after 2 slides. Okay. So first 5 rows from 2 to 6 is equal to presetting before we start our algorithm. Yeah, we say that we know only distance between S and S. Yeah, and other distances we don't know. It's false. So then we use Q to as a structure, as model for explode. So initially Q contains only S. Yeah. Then we pop S, as it says in 9 row. What does infinity means in line 4? It means that we don't know distance between S and other vertices. And if vertices V doesn't appear in the next operations, it says that there is no path from S to V. And by definition, we say that if there is no path between S and V, we have infinity distance between them. Logical, yeah? Do you understand, Masoud? Nice. Okay, and then we get from Q vertex U, and for all adjacent vertices, we say if their worlds explode, we set distance to them and set that they explode now. Okay? And then we add new explored vertices into Q and repeat our algorithm before Q become empty. Okay? So, for example, it's not interesting about this graph. Yeah? Here you see result of our BFS algorithm. We can remove edges that that didn't appear in our algorithm, and add only that appear when we connect vertex, this vertex, when we add this vertex into explored, yeah, we know for what vertex it adjacent, yeah. In this 12 row, we know that we remove U vertex, yeah? So we can say that parent of V is equal to U, okay? Then we say that this edge connects V with U, yeah? Okay, and let's see how it works. I tried. Yes. Does it work? Yeah. You can see. Okay, and from start. Yeah. You can see we have only one vertex at the start of our algorithm in Q. We remove it, and we see that these vertices adjacent to red vertex. Yeah. Then we say that yellow vertex connect with red vertex, and red vertex has distance to start vertex equal to 0. Yeah? Then we say that distance between new vertex one more than distance between these two start vertex. Then it's equal to 1. Yeah? And we repeat algorithm to other vertices. Yeah? And add them in Q, of course. Then, yeah, we add to Q. Then we repeat our algorithm to new vertices in Q. Now we remove center, yeah, and now in Q we have 1, 2, 3, 4, 5, 6 vertices, yeah, and we pop first of them that we have. This vertex, yeah? Then we see only one vertex is adjacent to this vertex, yeah? So we call it to yellow and find and say that distance from this vertex is more is one more than distance from this vertex to center, yeah? And it is equal to 2, okay? Then we repeat our algorithm, remove this vertex from Q. When we remove this vertex, we see 1, 2, 3 vertices are adjacent to this, yeah? So we call it to yellow. Oh.
The count is stored as a variable outside the loop, and you keep incrementing the
Oh.
count the distance value.
Oh, what's about distance here?
Distance value is a variable. It's
Distance now?
stored outside the loop. Yes.
Oh, yeah. We have no cycles in this in result picture. Yeah, and now we compute distance between vertices and center. And when we set number, we say that we know it's finite distance, and in line 6 we initialize distance of S. Oh, I have a question. Second, about 6 line. About 6 line. In line 6 we initialize the distance of S. We say that distance between start point and start point is equal to 0. Yeah? Okay. Then continue our clip. Yeah. We know that. 1 second. Nice. Now we know distance from this vertex to center, and we say that distance from this, and this vertices one more than this distance. Yeah.
We are assuming that the graphs are connected, right?
Nice remark. Of course, now we see picture of connected graph, but in common case we cannot know a priori that graph is connected. So if there are vertices that aren't reachable from vertex S, they have infinity distance from start, and they have the infinity distance in the end of our algorithm. But because we haven't been changing during our algorithm the elements U in array D. Yeah.
And I mean, generally, when we are considering algorithms of graphs, we consider the graph connected or.
When we use it.
I mean, like in general, when we use.
BFS.
Like when we study graphs, we are assuming that they are, it's one connected component, or it can have several connected.
We think that when we start our algorithm, we don't know is it connect. And there are different tasks in which, for example, we need to prove that graph is connect, or say that some properties, for example, is not true for graph. And we can use this algorithm, breadth first search, for understand connectedness of graph. And for example, to count numbers of connectedness component. It is useful to understand numbers of connected components. For example, in one application, okay, of course. And then we repeat it, yeah? We see, for example, for this vertex, we have 3 vertices that haven't been explored before it. And then we say that distance is one more than distance from this point to start vertex. And repeat it, yeah? And repeat for the next level, and repeat for the next level. And then when Q is empty, it means that we understand distance from vertex to all vertices in this connected component. And we understand which vertices are in other connected components, of course. Okay, let's swap to slides. We have 30 minutes. Oh, nice. It's about complexities, yeah? As we understand, we can count all vertices in Q, yeah? So we need to use number of V space, of course, yeah, in Q. And we need to use number of vertices space to erase D and erase explode, yeah. So it's theta, of course, yeah, because in the start we initialize arrays that have constant length equal to number of vertices. Then about time complexity, yeah. Of course, if connected component smaller than all graph, it's very unreal upper bounds. But we don't know anything about graph, and in the worst case, we spend all from number of vertices time to count all of them, yeah, in Q. And for all of them, we need to count every adjacent vertices, yeah? And number of adjacent vertices is equal to degree of vertex by definition. So when we, yeah, it is from 10 to 15, yeah? These rows say that we need to count all adjacent vertices to U, yeah? So we need to spend all from number, all from degree of V to get the answer of this cycle, okay? Then, yeah, we know that summary of degrees equal to twice number of edges. Yeah? And so we say that upper bound to our algorithm is equal to sum of number of vertices and edges.
Yeah.
Okay? Understandable? Any questions? Yeah?
I don't know if it is linear or
Quadratic?
can it be
Square? Of course, if we have space graph, yeah, if the number edges equal to linear of number of vertices, so upper bound says that we have linear approximation in big graphs. But if we have very full, nearly full graph, and we have number of edges, for example, number of vertices in square divided by 2, divided by 3, we get square
in worst case?
bounds. Yeah?
In worst case.
Yeah, of course. Of course, in worst case. It's bound in the worst case, of course, by definition. Yeah, remember that for all n, we need to get inequality. But of course, it is inequality. And if we have five, for example, seconds, yeah? And this inequality says that we can bound as millisecond. It's also will be true, yeah? So it's asymptotically bounds to number of seconds, for example, that we need to spend in our algorithm, okay? So, it was example. And exercises that we can solve. Oh?
Can you go back?
Yeah, of course. Back.
So why do we need to make the sum of all degree of
Vertices. Yeah.
why do we need it?
Why do we need it?
Why we need it in this?
Why we need it in this approximation? Because see in the example, yeah? For example, when we remove this vertex, we don't know what is vertices or which vertices are not explored. And we need to visit all of adjacent vertices and understand, is it explored? Explored. Is it explored? Explored. Is it explored? No.
Yes.
And then we add a Q. And we need to spend number of seconds equal to degree of vertex, of this vertex. But of course, when we visit these and these, we didn't do anything after that, because these vertices were explored between that.
For example, I mean,
Before that.
we just consider the edge, but not in, for example, the edge between two vertices.
Yeah.
We just go through the edge, we don't use it 2 times.
Oh, about 2 times. Use only 1 time, yeah?
Yes.
asymptotically, there doesn't matter is it constant equal to, but about we use edge in two directions or one. Of course, if we set in this vertex when we add it in a queue, yeah, when we set parent vertex, we can visit all adjacent that are not equal to this. Yeah. But about vertices that are dashed on the picture, when we set it, I think dashed vertices we visit from different endpoints, and we get twice number of edges. But of course, it doesn't matter. So we don't spend any time for this. Okay.
Yes.
Okay. And about exercises that can be solved by breadth first search. For example, if we have two vertices, of course, if we need to understand what is the shortest path between them, yeah, we can set one of vertices as start vertex, and start bfs, yeah. But when we use our algorithm, we need to understand, not only explore this vertex and distance, we need to understand what is the parent of this vertex. Yeah? For example, for these two vertices, we say that start vertex is the parent, okay? And then we repeat, when we repeat our cycle for this vertex, we say this and these vertices have parent equal to this vertex, okay? So we need to add in this implementation other array that contains parents of vertices, okay? And at the start it has 0 references, and at the end of algorithm this new array will contain reference to parents. And then when we end our algorithm, for example, if we want to find the shortest path from A to K, yeah, we know K has parents, yeah. This vertex has parents, this has parents, and it has the shortest path, okay? It's improvement like hash map with the value of vector. Yeah, you are right, Masoud. Yeah, like hash map. Yeah.
Can you go back to the algorithm?
Yeah. We need to improve add in this row add new array with 0 references.
Yes.
Then here we add another row that's set parents of vertex, okay?
Yes.
Then about finding components, as you say, when we have connected component. If we choose one of the vertex and start breadth first search, we visit all vertices in this component and we doesn't visit any vertices from other components, okay? So algorithm is simple. Yeah, we start with S from one of the vertices. Then if at the end of this we have vertices that we didn't visit, yeah, we start it from one of them and repeat it while we have vertices that have no that has no his own component that we visit. Okay? It's simple. Nice. Excellent. The shortest cycle. See, in this graph, we have two shortest cycle. And how to compute the shortest cycle? We can see on these two vertices, for example, yeah? Edges ES containing in this shortest cycle, yeah? So, for example, if we drop this edge from our graph and start BFS from E, we see that path from E to S equal to 2, yeah? And of course, if we drop edge and find distance between its endpoints, yeah, we can say that the shortest cycle that contains this edge is one more than the shortest distance between these vertices in graph that we get when we drop this edge. Okay? So we get for all edges, we remove it, yeah, and see what's the distance between endpoints of this edge by breadth first search, okay? And then we compare these numbers for all edges and find the smallest, okay? Yeah. Understandable? Yeah. Nice. Oh, nope. Okay, and about generalization, it's of course clickable. It's Wikipedia, it's article, and you can click at home on it. And of course, BFS we will use in different other algorithms. And but as itself, algorithm has some generalization that you can use in the your own task. Okay. For example, of course, in the big systems, you can't use traditional BFS because it has one stream, yeah, one stream realization. But of course, if you have big system, you need to parallel modes to get your algorithm in parallel modes to improve time complexity. And of course, when you open maps, yeah, and you search the best way to go to, for example, cafe, yeah, you of course say some service that you need to find ways and algorithms that are working on the servers are, of course, parallels algorithms. And of course, many of algorithms that we talk and that you talked with Mikhail, or you talked with other lecturers or assistants, has parallel mode, has parallel versions, and you need to understand this too if you want to work with this algorithm in your task when you will work in a company, for example, as Google, as Yandex, for example. Yeah. And about conclusions, yeah, of course, advantages that it's linear time, it's very quick for algorithms that solve for some tasks of the shortest path. We see that in the most cases we have a square or more or bigger complexity in other algorithms. And so it is easy to update in ways that we list this on this slide. Yeah, it's too important because if you have very nice algorithm but you cannot use it in parallel mode, it's bad algorithm. So BFS, breadth first search, nice algorithm, but of course you need to understand how to use your graph, because if you, for example, remove edges, add edges, as in this task, yeah? If, for example, you remove this edge and your parallel version remove this edge, what is it? It's mistake of algorithm. So when you go to other improvement of this algorithm, you need to understand what is the difficulties that appear when we change our algorithm. Okay? But of course, it has ability to update, and it's nice for this algorithm. And so about graphs, as you see, all examples have no weight on the edges. Yeah? Have no edges. Weight on the edges. But, for example, if you have transport web, yeah, or for example, network web, yeah, you need to understand how to work with weighting graphs, because, for example, when you have roads that are very useful by auto drivers, yeah, in the evening it will be very yeah, we have traffic on the roads, and we need to use it in the algorithm. And we cannot say that every edge have the same weight, yeah, equal to 1. What is parallel again? Masoud, about parallel realization, you can click on this reference and see Wikipedia or articles that in the end of the page in the Wikipedia. Or for example, you can open good website scholar.google.com and find breadth first search. Any scientific articles you can find on Scholar, but not all of them have access to common visitor. But, for example, you can see what is the implementation of parallel BFS here. Okay, and that's all by today. Do you have any questions?
You didn't talk anything about the scores and exams.
About scores and exams, okay. Firstly, I will send you information and references to GitHub or GitLab, or now we talk with assistants that will be better to us. And now I can say that we have we have 15 weeks, yeah, and on each week we have contest. And oh,
Every week we have
yeah, yeah.
every contest, one exercise or several contests?
From 2 to 5 exercise. As I remember, first contest contains 4 exercises.
Time to contest or no?
Yeah, it has a deadline. Oh.
Like last semester, there is a week deadline and you do in 1 week, or it's a time test?
It has the deadline,
Like
and
last semester? Like
yeah, yeah.
So we have 1 week to do the contest, and then we have another.
Yeah. But every contest has time deadline in 2 weeks.
It's not 1 week.
Hmm?
The deadline will be, for example, one contest, 2 weeks.
Yeah.
Another contest, 2
Yeah,
weeks.
yeah, yes. And we will have 3 tests after each module.
Same concept.
Theoretical.
The test is just quiz.
I think it contains questions with numbers of answers. It contains questions with big answer. For example, you need to say how we can use breadth first search to solve this problem. It can be one of the questions of test. So 3 times we will have theoretical tests and contest on the Saturday. And other weeks we talk about firstly about graphs. We'll continue on the next week and talk about deeps, first search, and topological sorting. And after first module, we talk about dynamical programming and algorithms from this part of programming. And so at the end, we'll talk about algebra and algorithms that connected with algebra. For example, we'll talk about modular arithmetic, and so maybe RSA, it's a cryptographic algorithm to send messages. But it will be maybe in the start of December. So there is a long way to get the destination of our work. That's all, I think.